Section 2.5 talks about physical applications. We have two applications we're going to be dealing with in this section and one application in the next section. So, first one deals with mass density formula for one-dimensional objects. So, given a thin rod, so think of a rod looks like this, but think of it as infinitely thin, running from A to B. Let rho of x denote a linear density function. What linear means, it is one-to-one. It is the same correspondence, like kind of like y equal a straight line, as x increase, y increase. And they do that in a linear fashion, kind of like y equal mx, where one-to-one correspondence, that is, depending on the slope. But the change of rate in this case is constant. It doesn't change, the slope of the line. So that's fixed. Unlike y equal x squared, quadratic, or that as x increase, then y changes drastically. Here, the change is linear, which means it's the same anywhere you are on the line. Well, the density of the rod at a point x in the interval, right? So rho is dependent on x. Then the mass of the rod, the mass of this whole rod, will be simply the integral of this density function with respect to x. And remember what this does, if you recall, what this does, this slices it into an infinite amount of thin slices and sums them up. So, find the mass on one-dimensional. Well, that's fairly simple. All what you have to do is say the mass is the integral of rho of x dx from A to B. In our case, that's the integral. A wire that is 2 feet long, 0 to 2, x squared plus 2x dx, that's in pounds per feet. The only thing in this section you got to be careful with are the units. And they really don't mess around too much with the units. So, make sure it's feet to feet, and inches to inches, centimeters to centimeters, and meters to meters. And the mass is fairly simple in this case. X cubed over 3 plus 2x squared over 2 evaluated from 0 to 2. That is 8/3 plus 4. Or simply 20/3. Another example, a metal rod that is 8 inches long starting at x equals 0 and has a density function. Again, they're matching. We say the mass is the integral 0 to 8 e to the 1/2 x dx. And we know what that is. That's e to the 1/2 x divided by a half or multiplied by 2 over 1 evaluated from 0 to 8. E to the 4 minus e to the 0, which is 1. And that's basically it. Now, once you figure out what the mass is, you could use all different sorts of what's needed. You could figure out the weight on Mars, the weight on the moon, the weight on Earth, depending on what gravity is and those, but you need the mass first. So you're just finding the mass, which is the first step in the application. Again, a ruler that has 12 inch long starting at 5. So this is the variation between using calculus versus non-calculus. If I want the mass, that's the integral starting at 5 to 17. The units are matching, of natural log of x plus 1/2 x squared dx. So if I look at this piece, if I let u equal natural log of x, du is 1 over x dx, dv is dx, so v is x. So pretty much what I'm doing here, I'm splitting this up. The first piece is going to give me x natural log of x. minus the integral. If you multiply those, they cancel out. And this is simply x cubed over 6 evaluated from 5 to 17. So that is 17 natural log of 17 minus 17 plus 17 cubed over 6 minus 5 natural log of 5 minus 5 plus 5 cubed divided by 6. Whatever that is. Now, another application that's going to come up in your next course, if I'm dealing with a circle, let rho of x be an integrable function representing the radial density of a disk. So if you look at these circumferences, that's what that is. And if you think of it just of a disk of radius r, then integrate from 0 to that r. The circumference times the density. Well, you take the small circumferences as they get bigger, and the integral will add them all up. And that's how you get it on a disk. Well, this is 2 dimensions, and in the next class you do 3 dimensions, which is pretty much where the application we talk more about what the density is, and here the density is fixed, there the density is varying, and so on and so forth. So for the following exercise, find the mass of the 2-dimensional object that is centered at the origin. A frisbee, well, we know what that is. That's a disk. Radius 6 inches. Well, here the mass is the integral 0 to 6 of 2 pi x e to the negative x dx. Integration by parts once. Let u equal x, du would be dx. Let dv equal e to the negative x dx. V will be negative e to the negative x, and that's going to be, the 2 pi is a constant, x, negative x e to the negative x, so that's going to yield the product of those, x e to the negative x minus the integral, and when you multiply those, that becomes plus e to the negative x dx. When you integrate that, you get minus e to the negative x, and that's basically it, evaluated from 0 to 6. Just be cautious that e to the 0 is not 0, it's 1. And you end up with 2 pi times negative 7 e to the negative 6. Of course, you could leave the answer like that on a test or a quiz. And there it is. And another problem, just to make sure that we're getting this. And I'm more interested in you doing those, I mean, to practice the integrals more than anything. Here we're talking about a disk with an inch, with a radius of 3 inch, and the density function is natural log of x plus 1 dx, and we should know that anytime we're dealing with a natural log or inverse direct function, we let u equal that. dv must be x dx. I'm forgetting the dx. No, I haven't. Yep, I'm right. So that is, v would be x squared over 2. So this is going to be, let's see, the product of those, x squared over 2 natural log of x plus 1 minus the integral of the product of those. The 1/2 you take up front, x squared over x plus 1. That is an improper fraction. So that is negative 1/2. And if I integrate that, that is going to be x minus 1 plus the remainder And if I integrate that, that's simply x squared over 2 minus x plus natural log of absolute value of x plus 1, evaluated from 0 to 3. So substituting 3 in, 9 halves natural log of 4 minus 1 half plus 9 halves minus 3 plus natural log of 4. Of course, you can combine those. If you put a 0 in, few things are going to 0 out. And natural log of 1 is also 0. So that would be pretty much... Okay, it seems I messed up. I forgot the negative 1 half. This negative 1 half was multiplied by those. Right? It was negative 1 half, so that's negative 1 half is multiplied by those. So really quick. There we go. And when you put 0, that's going to be 0, 0, 0 times a half, so that's a 0 automatically. And whatever that is. Okay, now we get to a more interesting application. This is something that we are going to use all throughout our next course and the courses after that. And I'm doing those problems out of order for specific reasons. Suppose you have one of these springs. This is what we call natural length. So 0 doesn't start here. 0 starts from the stretching or the compressing of the spring when you let it stand at its natural length. So x is either the stretching or the compressing from when it was left alone and it took its natural length. That's what this x is. The key is finding this force function, and once you find it, if work is fixed, the force is fixed, if the force is constant, then I really don't need any calculus. I could just multiply distance times the force. That gives me the total work done. But if the force is varying at different x's, I'm getting a different value of the force, then I have to sum them all up, find the force at every fraction of the second, and add it all up. Let a variable force f of x move an object in a position for x from A to B, then the work done. So keep in mind what A and B are. The work starts from that A right there, from wherever you stretch or you compressed. The units you want to be cautious with. Now, you want the units to be in meter. If on a test you leave them in inches, that's okay, I don't mind. But if you really want to get the units, you want to get the newtons, you want to get the joules, you really want the meters, the kilograms, not pounds, and so on and so forth. So here's the first example. A 12-inch spring is stretched to 15 inches. We were at 12. A 12-inch spring is stretched to 15. So the length of it is 12. That's what we count as our 0. And we go to 15. That means x is really 3 inches, or simply every 1 foot 12 inches, that is a fourth of a foot. Again, if you leave it in inches, I'll let it slide, that's not a problem. What is the spring constant? Well, F equal kx. The force applied in this case is 75 pounds. K is the spring constant, and that's what you need to find first every time. Once you find that you're set, you just put it in there and you integrate and everybody's happy. X is 1/4. Again, if you use 3 inches, that's not a problem. Just write the units in. And in this case, K would turn out to be 300 And in our case, it is pounds feet. And if you were to leave it as 3, you would have said 25. You divide by 3, 25 pounds inches. And it doesn't matter. It's the same thing. Just you don't have to match the units in the back of the book. As long as you're consistent, you're fine. Here's another problem. A 1 meter spring requires 10 joules to stretch the spring to 1.1 meters. So we have this spring and it is 1 meter long. We're going to stretch it to 1.1 meter. But if the original length is 1, then we really only stretched it 1 meter. We stretched it 0.1 meters. We stretched it from 1 to 1.1. X is 0.1 meter. How much work would it take to stretch it from 1 to 2? Well, here we go. A 1 meter spring requires 10 joules to stretch it. Joules is not force, joules is work. The work here, stretching it from 0 to 0.1 of f of x. Well, f of x in this case is kx. Since we don't know what the force is, we're going to say, well, okay, that's the force dx. And we know that was what? That was 10 joules. Well, isn't this kx squared over 2 evaluated from 0 to 0.1? And wouldn't that be k over 2 times 0.1 is 1 over 10 squared? And k over 200 equals 10j. And then we could say, well, look, k is 2,000. So now we know the force is 2000x. Now we could figure out the work required for any length or any type of stretching or compressing. The hard part is figuring out what k is, and that's always what you want to find. That is, that tells you the stiffness of the system. And once you know that, you could pretty much predict the work done in doing whatever it is. And again, remember, those springs could vary from a mechanical pencil spring to a spring on a car, which is a shock, Some are denser than others. Excuse me. A shock absorber is compressed 1 inch. So X is 1 inch, which is 1 over 12 of a foot. By a weight, the force is 1 ton. What is the spring constant? F equal kx. The force is 1 ton equal 1 over 12 k times 1 over 12. So k is 12 tons feet. Remember, if using tons, it depends whether you're talking about the metric system or none. The English tons is 2,000 pounds. If that's what you want to use, but you could leave it like that. That's not an issue. And the American, I believe it's 1,000. Let me double check. Yeah, it turns out the American ton is 2,000 pounds. The British ton is 2,240. I just Googled it. Well, it doesn't matter. You could leave it in tons if you want. You could write it as 2,000, 2,400 pounds, whatever. Doesn't really matter. Now that we got this idea of force out of the way, let's apply work. Find the work done on the following problems. Find the work done with a constant force of 12. If the force is fixed, I'll show you 2 things. And you move a chair from 0.9 to 1.1. X is the distance, that is 0.2. It is in feet. So we're set there. We really don't have to convert that. And I could say work equal force times distance. Work is, the force is 12, distance is 0.2, so work is 2.4 pound-feet. Now, if you decided, wait, why didn't we integrate from 0 to 0.2? 12 dx. Well, you could have. That will be 12x evaluated from 0 to 0.2. That would be 12 into 0.2 minus 0, which is 2.4 pounds-feet, if you really want it. But if the force is fixed, then you really don't need calculus, because along all of these, no need to slice them into an infinite amount of subintervals and atom. They're 12 all the time, and they're not going to change, the force that is. And similarly, oh, come on. Here we go. I could integrate here too, but the same thing. What is the work done by lifting a 20 kilogram? Force is fixed. That's not changing. The child is not changing its weight. From the floor to a height of 2 meters, x equal 2 meters. Okay, well, work is, again, you can integrate if you wish. I don't see a point in that if the force is constant. If the force is varying, then yes, you do need that. Times 2. And work turns out to be 40 kilograms meters. Now, the one thing that's working against you when you lift that, note that 1 kilogram equates to 9.8 newtons. So you could leave the answer like that. There's nothing wrong with that. Or you could say, look, we want kilograms to newtons, and each one of those is 9.8. And now my answer is 9.8 times 40. Let me figure out what that is really quick. That is 392. And newtons times meters would be joules. Again, you don't need to do the conversion. What I boxed first is fine on a test. And the last example we have, compute the work done by a force. This force is varying. As you see, it's 12 over x squared. As you move further, as x increases, the force is decreasing, right? It's inversely proportional to the square of the distance from the starting point. We're going from 1 to 2 meters. Work is the integral from 1 to 2. All the units are matching. That is 12x to the negative 2. Add 1 to the power, divide by that. One over 2 minus 1. That is negative 12 times negative a half, which is 6. And the units are newtons meters. Automatically, that is joules. And that's pretty much it for this section.